So just a few housekeeping announcements before we get started. The Protein Society will be hosting their 37th symposium in Boston this summer, July 13th through 16th. And I just want to point out that a feature of this meeting has always been that undergraduate researchers are featured prominently in it. And we often hear stories of people who their first real scientific conference experience was when they went to a Protein Society meeting as an undergraduate. And that was usually an inspiring experience for them. And so we hope you'll join us. We have a wonderful program, and we hope that we'll see you there. And I just want to point out the Protein Society sponsors a journal, Protein Science, edited by John Curian, who's a graduate of Juniata College, one of the small colleges being represented today. And the journal is doing very well. We have an impact factor of around 7, and we hope that you will consider submitting your best work there. So with that, let me just say again, thanks for attending. And I'm now going to turn it over to our session chair, Ellis, to introduce the first speaker.
Thank you, and thanks to the Protein Society for letting us do this. As you'll see, we've got a variety of speakers, and in fact, Jessica Bell is going to lead off, so let me introduce Jessica Bell. So Jessica, the floor is yours.
Thank you. So today we've separated out the webinar into 3 parts. We'll start off with why we want to consider cures, some examples of protein-centric cures, and then cures and a little bit about cure design. Then we'll take some questions and do some answering, and we'll move into part 2, looking at some pedagogical research related to cures, different types of implementation of cures, and finally how we can broaden our impact by using shared equipment, etc., as part of the faculty involved with cures. And we'll end with hypothesis development and looking at the role of curiosity as part of that very important component of cures. So let's get started. Why cures? So if we think about why cures, spoiler alert, the answer is all in the title here. It's all about the undergraduates and getting them into research. So if we look at how we are growing in terms of our STEM educated workforce, we are going to increase by about 11% over the next 8 years as this prediction goes from the Bureau of Labor Statistics. That's 2 times faster than all other occupations. So as educators, we need to be thinking about how do we attract, retain, and train the best STEM workforce to meet this demand? The answer is to involve them in research. As undergraduates, we need to think about what influences them to choose a STEM-related major and what also helps them to stay within the STEM-related fields. So research can answer many of this. Studies from the apprenticeship model of research show that exposing and engaging students to research leads to positive outcomes, such as developing their skills, applying the scientific process, that is that central part of how we do our science and generating our knowledge. It becomes embedded in how they think, and they develop a great understanding of how to apply it. We can also see that it helps them identify as scientists and also to persist in the sciences. And so they become these purveyors of science, whether they remain in the field or if they move abroad from the field. So research, that is that discovering and disseminating of knowledge, becomes a driver for them staying in STEM. And so if we want to have more students coming into STEM, we need to have them more involved in the research. And here are a few examples of some of students that I've had within in my own laboratory that have gone on to great careers in STEM, from industry in Illumina and Ignite, and some to master's programs, PhD programs, and also to the healthcare fields, such as MDs. So if we look at the evolution of STEM curricula, starting in the 90s and through the 2000s and culminating in 2011 with the Vision and Change report, we see and we can trace this transition from covering content to looking at concepts. And along with that, the emphasis on skills, that is these competencies. And right at the top of the list is applying the scientific process. That's research. And that's how we're going to engage our students and make them most successful. If we look also at the Boyer reports, the first one coming out in 1998, that was important in terms of emphasizing the teacher-scholar model and encouraging and urging, especially R1 universities, to make research, and in this case, the apprenticeship model of research, a hallmark of undergraduate education. In 2022, October, the Boyer report had an update, and it came out and it put into that what they termed an equity excellence imperative, which is a belief that excellence and equity are inextricably intertwined, such that excellence without equity, that is privilege reproducing privilege, is not really excellence. And that equity, just merely giving access without excellence, is an unfulfilled promise. The commission went on to outline 11 provocations of equity excellence that they hope and mean to stimulate the institutions and also culture to impact change. And I'm pointing out just one of these provocations at the top, access to excellence, as it pertains to our topic today. Here they ask the question, how can we render high impact practices such as CUREs, which are hallmarks of excellence in education, accessible to all? And the strategy that they come up with, and that I endorse, is making those evidence-based or high impact practices part of the curriculum, not an extra or an add-on that students need to sign up for or find those experiences. And that by embedding these high impact practices, or HIPs as they're referred to in this report, into courses, we can ensure that all students have experience with them. So that brings us to our topic for today, and that's CUREs. We want to move from the apprenticeship model where we have the one-on-one interactions between mentor and mentee and make that a core part of the curriculum, taking that into our lab-based courses and expanding our impact to include all. So the growth of CUREs, both in development and adoption, suggests that if we look at the diffusion of innovation theory, we're moving from the early adopter phase to the early majority phase. And this is driven largely in part by the success of this pedagogy in engaging and in increasing the positive outcomes for our students. In looking at the research model of apprenticeship and comparing it to CUREs, we see many of the same hallmarks of research embedded in CUREs, and therefore we also see many of the same positive outcomes. And this is a very active area of research in that we're looking at not only how it impacts students and what's coming out and what's needed to have those positive impacts, but also we're looking at faculty and how it's impacting them and improving their motivation for research as well as their progress within research. If we break it apart, students benefit by having the CUREs embedded in their curriculum as it now becomes a normal part of it. They don't need to find extra time outside of having to perhaps commit to work or to extracurriculars. It's in their curriculum. It's going to be part of what they're normally doing. For faculty, same benefit. It's part of the curriculum. If we think about what we need to do in order to be promoted and to receive tenure, we think of scholarship and teaching, service, etc. And if we take two of those elements, scholarship and teaching, and combine them, now we have 2 times the outcome for an effort that we put in, and it's helping us to get to a goal that we want to achieve. As part of this, as faculty, when we're having to develop these new curricular components, we also have to think about the investment. So we need to invest time, perhaps funds, and also alterations to what we're already doing within the classroom. And so in terms of time, perhaps it's recruiting or training TAs or even instructors. Funds, it could be supplies to do the research or to bring in a TA to help with that type of course development. And then in the development part, we have to think about creating the right scaffold so that when you deploy it the first time, you'll be successful and it won't be chaotic. Although no promises, sometimes chaos ensues. So as part of this and as part of making this more readily available, we need to look to what others have done. So we have protein-centric cures that are available for those in this field to adopt, and we'll talk more about those in the next presentation, but also looking to the literature. And that combined, this community of those who've already adopted or who want to adopt, this is a vital support network for those of us who want to transition to and transform our curriculum. And we'll talk about more of that throughout this webinar. So what is the current status of cures? What's out there? There's a great review that came from Buchanan and Fisher that was published in November 2022, which looked through the peer-reviewed literature and found cures that conform to the field's accepted definition of what a cure should contain. And they identified 242. And you'll see that over the time frame of 2000 to 2020, which was their study's timeframe, you'll see a great growth, especially starting in 2014. That's actually the year that the cure and name was coined. And it's sort of like the Great Wave of Kanagawa, in that we see that as we increase the cures, there's a sea change in terms of how we engage our students within the research fields. Looking a little bit more closely at the data coming out of Buchanan and Fisher, you can see that in this graph, again, it's the same years 2000 to 2020, but now we're looking at them divided into the cures being implemented to first-year students or at the beginning of their curricula versus those who are exposed to cures as they are in their more upper division or advanced level courses. And cures are still more heavily weighted toward those advanced courses, but we are seeing an increase in the introductory cures, a great way to attract and retain students in STEM fields. And this is primarily due to some of those first-year research experiences or FIRE programs, hallmarks of, for instance, UT Austin, UTEP, and College Park, for just a few examples. If we look at how cures are in this particular study divided amongst disciplines, we see that biology has quite a few. And for protein-centric cures or protein chemists, if we look at the biochemistry aspect here, they found 19 in the peer-reviewed literature, and most of those are heavily weighted towards the advanced courses or the upper division courses. And so there's plenty of room for growth and for others to add to the wealth of cures available for those to adopt and use. And so in the next talk, we're going to talk a little bit more about protein-centric cures and what's available as some of those both reviewed here and even newer ones that have just been developed and deployed. So with this very brief introduction on why we should consider cures, what kinds of impacts they have and why we want to deploy them to have those positive student outcomes, I'm going to now move into acknowledging who I work with and how they have helped me. That is the people I work with at USD, the biochemists, our supports people, and most importantly, our students. And a full disclosure, I am part of the malate dehydrogenase cures community, which grew out of some pedagogical questions we had, and so it was supported out of NSF IUs. And shown here are a few of my colleagues within that network, the MCC, and many more who are not pictured. And then throughout the talks, we've developed a QWERTY code that allows you to access all the references that we're using throughout our talks as a compiled list. So go ahead and capture that, and we'll also share with you a tiny URL where you can access that. So with that, I want to turn it over to Dan Dries, who is going to talk about protein-centric cures, some exemplars.
Thanks so much, Jess. I had my eye on the Q&A. I didn't see anything in there, but just to remind folks, if you have questions, feel free to drop those in the Q&A box on the webinar. So thanks so much, Jess, for the passing it off to me. Jess is going to be my partner in crime as we talk about some examples of protein-centric cures. And we're going to give you a smattering of some of these. We especially pulled out those that that kind of fostered this cure community aspect that Jess mentioned earlier. There are a lot of cures that are kind of individual labs, and the ones we'll share with you here are learning communities among faculty. And so one of the first we'd like to share with you is one that I'm a part of, which is Basel Biochemistry. Basel stands for the Biochemistry Authentic Scientific Inquiry Laboratory Community. It's supported by NSF grants at a number of institutions. And the idea, the URL is down in the bottom left. Again, that's on the list of resources that if you go to your chat, you'll see that Chris dropped a tiny URL in, and then that same QR code that Jess had shared with you earlier. And so the idea behind Basel is that there are a number of protein structures in the protein data bank for which we have structures through structural genomics initiatives, through other screens, and yet we don't have that no known function is assigned to them. And so the idea behind Basel then is to try to find, hypothesize, develop, and identify, experimentally verify functions of these proteins. So the idea then is, can we take advantage of web-based bioinformatics tools to try to pin a function on some of these proteins? And so students walk through 5 modules on the front end. That's a kind of a virtual lab. I can share with you that right now I'm in the middle of running a section of a biochemistry lab remotely for students, and I've used this. It's worked really well. I've done this with some other virtual tools, simulations and things. And so they themselves are hypothesizing protein function. I also use this transition, allowed the transition to remote instruction really well during the pandemic. They were quick to respond, the Basel community was. And so students start off doing structural alignments of active sites, trying to get a general idea of what these things might be doing. They do protein blast searches and use Interpro to identify domains and understand what those domains, what those functions of those domains might be. Then they do a global structural alignment, and they finally conclude in a virtual space, at least, with doing molecular docking studies using SwissDoc to come up with potential substrates and small molecule inhibitors. Then they go into the wet lab, and many of these are already subcloned into vectors for easy expression in bacteria. And so they can purify their protein, determine concentration. They can run SDS page gels. If antibodies are available, they could do Westerns. And then, of course, they ideally they conclude with some sort of activity assay. A lot of these proteins are have substrates that can be easily adapted for colorimetric assays. For example, a lot of hydrolases have colorimetric substrates to make that relatively inexpensive, or at least less expensive. And easier to perform. So, Jess, would you like to share about the MCC, please?
Thank you, I would love to. So the malate dehydrogenase cures community grew out of some pedagogical research that we were interested in addressing. That is, some aspects of the core elements of cures. How can we assess their impact on students and some of those positive outcomes? And so out of that grew a community which then collected data to address those questions. And that community is the MCC. And now it is a national network of faculty who are utilizing the malate dehydrogenase enzyme as the model system within their cures in order to engage undergraduates in research. And so the pedagogy is supported by the NSF IUS grant, and the growth and support of the community is supported by an RCN UBE grant also from NSF. And in the upper left-hand corner, if you're interested, there's a QR code there that talks about some of our pedagogical research in terms of a little video that we had done for a showcase. So here's some brief things about the MCC. So along the bottom, these are snapshots from our website, which show you some areas where we have resources available for the community. So starting with the left-hand side on the bottom, thinking about what are some ideas? How can I use malate dehydrogenase? What's out there that's known that might be a question that my class or our curricula wants to address using this model system? We have lots of resources for teaching in terms of syllabi, different files that you can utilize as introducing malate dehydrogenase into your curricula, but also rubrics for assessing how are my students doing and when I'm deploying a cure. Part of the RCN UBE supports fellows within the program so that you can become part of the community but be supported, have a mentor, some help with supplies, constructs, etc. And so there's a fellows program for the next few years as part of the RCN UBE. And then there's a national network, so you can tap into people close to you or further away as a support as you begin to develop and deploy your cure. In terms of tangible resources, there are plenty of constructs and videos that are brief protocols that you can use or your students can use, and then also tutorials. And in terms of literature, we have a fabulous community that has taken it upon themselves to read a lot of the literature and summarize it. So as you're jumping into a new field, you can tap into that and get some really good ideas of this is a ripe area for our research to go into, and that's what our cure could do. And then in the center, if you're thinking about, well, what's so special about malate dehydrogenase? I would argue what is not special about malate dehydrogenase. There are so many things that we can do with an enzyme that we expose our students to as part of the normal curriculum, but having them think about it in different ways. And so we think on terms of post-translational modifications, interactions, genetics. We've been doing CRISPR knockouts recently. So I think the possibilities are endless, only limited by what we can think up. And so if you're looking for a cure, MCC is more welcoming in terms of community and support than I hope you'll ever need.
That's wonderful. Thanks, Jess. A third one that is kind of intriguing is this design to data cure, which is out of Justin Siegel's group at UC Davis. And the idea is that if you want to understand protein structure, site-directed mutagenesis is a common way to do that. And yet, if you want to do a bunch of mutageneses, of course, it takes a lot of person hours to pull that off. And so Justin said, well, why don't we see if we can crowdsource this? And so he began with about 100 point mutations in beta-glucosidase and found out that this was scalable, perhaps as a cure. And so this is now supported by an NSF RCN UBE award. And the idea is that there are a bunch of different plug and play modules where students can explore protein structure. So if you go to their webpage, you'll see some student activities that you can engage in, much like what Jess had shared that MCC puts out, the different kinds of experiments that students might be able to pull off. And again, there are different entry points into this project, like a lot of cures are set up to do. There's also a robust faculty network where folks will support the development of offshoots of that or the implementation of the cures. And the third is this D2D database and app. And I think it's worth kind of talking a little bit about this. The idea is that if we can crowdsource, the idea behind design to data is that if there are sufficient structures, or I should say sufficient data, then perhaps the team could take advantage of that large data set for machine learning and artificial intelligence to think about things like enzyme design or small molecule design. And so that's where this group is largely targeted to. And so students under this cure will generate through site-directed mutagenesis, will generate mutants and categorize them for all sorts of things, including protein expression conditions, thermal stability, of course, catalytic efficiency, and then deposit that data into a publicly accessible database. And so folks can both come into this from the experimental wet lab side or from the experimental computational side. And the goal, again, is to have sufficiently large data sets to then move this into a machine learning environment for further exploration. Another one that is worth mentioning is a group called Antibody Engineers, and they have a bunch of different activities, but one that we thought might be worth drawing your attention to is antibody hackathons. And so the idea behind this is having a large crowdsourced group of folks come together and create cures and cure-related materials from an antibody engineering perspective. And so if you click on the hackathon, you'll find out that actually just this week registration opened for the summer's hackathon that takes place in August. You can see it at the bottom there, August 7th to the 10th. So if you're interested, hop in there. You don't have to have a new idea. You can bring new ideas. The idea behind this is that some folks will hop on existing projects, others will contribute to new projects, bring new visions to it. Some of the sample projects include doing yeast display as a relatively inexpensive, low-cost way of doing antibody screens. Another project is looking at the interaction between existing commercial antibodies against the spike protein and trying to understand interactions with as new variants pop up. There's another effort to come up with an antibody generation game, so exposing folks to what the drug design process looks like in a gamified way, so that students can get exposure to that. So all sorts of different ways of thinking about antibody engineering. And then lastly, we wanted to share with you CureNet, which is the MetaCure, right? This is a database where a lot of folks have deposited their cures. There are lots of resources. You can see from this screenshot that there are kind of theoretical instructor resources. So why cures are useful as a pedagogy and why you can use them for research. But there's also all kinds of other resources out there, particularly for certain members of the CureNet group, or for protocols and things to share with students. But then you can have a searchable database of various cures that are out there. You can search by discipline, as you can see in the upper right-hand side. You can search by competency. You can also search by the nature of the research, right? Applied research, field research, wet lab, bioinformatics, things like that. So it's a really rich resource to kind of go in and see what's already out there, and maybe even for inspiration for developing your own cure that might be supported through a bunch of different means. And so with that, thanks for your attention. This QR code will direct you specifically to those URLs in that document that were referenced in this particular part of the presentation. Same with the tiny URL, it will take you to a bookmark and to those hyperlinks. And I do think we might have a minute or two for questions if anything popped up in the Q&A. All right.
As far as I can see, there's nothing in the queue in the questions. So
thanks, Regina.
Yep.
I will then pass it back over to Ellis, who's going to talk with us. Ellis and Chris will be talking with us about cures and cure design.
Okay, thank you, Jess and Dan. Hopefully by now everybody's got the idea of why cures are good and the rich diversity of cures that are out there and can be developed. One of the things we've been doing over the last few years is thinking about the key components of research that should be represented in cures. And I'm going to spend a few minutes giving you sort of a framework for how we've scaffolded the cures that we've been working on. And in fact, as you'll see, a lot of cures are scaffolded this way. But so I'm going to approach this from the perspective of backward design of a cure, but I wanted to highlight one of the things that got me and a lot of other people interested in these. It's a quote from Tom Check that was in an editorial he wrote in Science back in 2003, and he wrote, hands-on research experiences though inherently inefficient with respect to faculty effort per student, are strikingly effective in their impact on young people's lives. And I think, as Jess pointed out, that's one of the things that really has driven this whole cure community and development of cures. The other part I'd like to make about cures is they shouldn't just be for scientists and science students. There's really a lot everybody can learn. I was talking with Jess this morning. I've had music majors take my cures, and in fact, one of them is now lead singer in the Metropolitan Opera, and I still occasionally get comments from her about the research experience that she gained in the cure that I was teaching at the time. So yes, they're good for science students, but they're good for everybody from the perspective that the more people understand science, the better. So we took the vision and change as a starting point in this, and we looked again about the list of attributes of scientifically literate students. And as Jess pointed out, the ability to apply the process of science is broken down even further into understanding the relationship between science and society, communicating and collaborating across disciplines, applying quantitative reasoning, using modeling and simulation, and making use of the interdisciplinary nature of science. And as you'll see, as we develop some specifics about cures more, all of these come into play in cures. And so it's really giving a very rich education to students by using the cure process. So we've approached this from the reverse design, the backward design, which a lot of people use in course design. But, you know, you identify the desired outcomes, you decide how you're going to decide whether or not you've succeeded, and then you plan your cure. And so talked a little bit about what a well-educated student should be able to do. I'm going to break that down even more by thinking about what really is research. And then we're in the process of developing rubrics, community-developed rubrics that are brought in all types of institutions, from community colleges to PUIs to Research One institutions, to give us feedback as to, you know, what we really, how will we know that students have achieved the goals we're setting out for ourselves. And then, and I'm going to focus on this a fair amount in this talk, what we call modular and full semester cures, and how you can incorporate research into a course. And then at the end of this first session, we'll talk about some sample curricula. So we looked at the various components of research and what should be in a cure. And it starts from the idea, if we start at the bottom and work our way up to the top of the pile here, the ability to explore a big picture question that is relevant to outside stakeholders. And of course, it's research, so it has to have the potential to create new knowledge. As research scientists, we all know that we depend upon the scientific background. So a cure should contain some component of exploring the scientific background. We develop hypotheses, and from the hypothesis we've developed, we make predictions as to experiments that we might try. We construct a proposal. We all have to submit them to NIH and NSF or wherever, but that ability to logically put together a proposal is an important part of research. Then, of course, we have to do the experiments. It often involves teamwork, collaboration. We'll talk especially about teamwork or collaboration as we go through this webinar. We collect and record data, and we have to look at the reproducibility of the data and the data analysis, etc. We have to be able to draw evidence-based conclusions, and we have to be able to communicate the outcomes of the research, in essence, back to the stakeholders, which is why this comes back. And those stakeholders could be in a variety of contexts. So taking that as what the research process is, we put together a list of what the well-educated student should be able to do in terms of each of these components. And I'm not going to read all the way through them because you'll be able to look at these all later, of course. But in relevance, the student should be able to articulate what basic information or applied information or societal issues their research will address. And you need to, and the student benefits by being able to communicate that to both a lay audience and a professional audience. At least in our lab and our cures, we talk about the elevator talk, and everybody's familiar with that.
John, this is
Can you communicate what you're doing? They should know the background literature, annex, more and more, and get ideas from and bases as well as the background literature. Gaps in knowledge exist. A big part of research in a cure is that hypothesis and understand, to be able to falsify it, that it's going to make predictions. And this hypothesis lacking in some of the cures that are out there. And then they learn a lot of useful skills in terms of producing a proposal. This gives a little bit more detail to the other aspects of this. And again, I'm not going to just read all the way through it in the interest of time, but they're all up on the web and things that you have access to. So we put together cures in terms of three sort of major blocks of approaches. So it's sort of described here in this sort of Venn diagram with research in the middle at the intersection of these aspects. So relevance, hypothesis, development, predictions, proposal, background are one aspect. Designing and conducting experiments and looking at experiment reproducibility is another. Then data analysis and presentation. And in each of these areas, we've developed rubrics that allow you to think about how to assess. And these are generic. And hopefully, if you decide to get into this, you'll be able to take these rubrics and customize them for the particular research that you're doing. But it sort of gives you a coverage of the various components of the research that we feel should be in a cure. Now, this diagram is for a different point. I mentioned earlier full semester cures and what we call modular cures. And this, again, this is a link to the NSF video showcase video that Jess mentioned. And this talks a lot about cures and developing them, but it also talks about this difference between modular and full semester. And it's often easier to start a cure with a module. One of the things you often run into when you're trying to start a cure is your department has things that it's telling you you need to include, but you want to include a research component. So these are usually 6 or 7 weeks, whereas these are the full-blown semester cures. And some of the pedagogical research has shown that there are distinct benefits that come from even having a modular cure. And anecdotally, a lot of the community that have started with modular cures rapidly then segue into doing a full semester cure. Okay, and then again on the web, we've got sort of templates for organizing a full semester that shows you a way you can lay out these components into a semester for either a full semester or for a modular cure. And you'll see all of the elements are in a modular cure. There's just less emphasis of them, obviously, if you've only got 6 or 7 weeks instead of a whole 15 weeks. And on that note, I'm going to turn it over to Chris Berndsen from JMU. So Chris, I'm going to stop sharing, and Chris is going to provide some detail of some of the cures and the way some of these things work. So I'm going to stop sharing. And Chris, the floor is yours.
All right, great. Thanks, Ellis. I appreciate the time and the introduction. And as Ellis mentioned, I'm going to move forward and talk about moving from design to sort of how these look like when they're implemented, and some of the things that I've learned along the way in implementing some of the cures that I've been involved with. And I'll give you examples of a cure that I've done in a biochemistry lab, a biochemistry lecture, as well as a general chemistry cure. So the biochemistry cure that I teach is a 200 level course, and it's not for science majors, it's for dietetics and kinesiology majors. So they're really focused on some different outcomes than maybe you might have for chemistry majors or biochemistry or biology majors. And so the way we lay this out is in our 14-week semester, we actually do 2 projects. In the first project, we spend our first 2 weeks doing a little bit of background. We learn how to use the pipettes, we start making quantitative figures. I work with the JMU libraries to start teaching students how to search literature. We make some buffers, so really sort of fundamental lab skills. And then we jump into the first project, which is purifying proteins directly out of sweet potato in this case, because these are dietetics majors. Anytime you can connect to food and show them the relevance in this case, they really love that. So knowing who you're teaching and knowing who your audience is can really influence the type of project that you're doing. So these students, we expand a bit on their technical skills using that purification. And along the way, we're developing a plan for how they're going to characterize the activity of this amylase. And we try to connect it to the functions of these enzymes affect the food flavoring or the nutritional value or the way that the fruit or vegetable might be stable as it ripens or starts to decay over time. And eventually they make a proposal and a plan to then collect some activity assay data on this enzyme that they purified. And then they present those findings and what they learned. And then we start a second project, which is focused on gluten. And this is a more of a structure function project and understanding how the protein gluten affects the properties of bread dough and other ways that you can apply or see gluten in food. And they're trying to do everything that they've already learned, but I give them more freedom and I sort of just manage them rather than actually telling them what to do. And then they repeat this again. So we've got 2 projects that check the boxes in terms of doing the things you would want to see in a cure. But one's more hands-on and getting the students up. And then the second project, they really drive it on their own. This is one of the first projects I started developing, but I eventually moved into my Biochem 1 lecture because I didn't like to teach out of the textbook. And so the course that I teach every semester. It's 1 section and has between 75 and 125 students per section. And I'm the only instructor and I don't have any graduate students. So it's just me in the classroom. And I really wanted to get away from telling the students what to do and to be down and working with them. So we have topic weeks that we cover in our 1 semester biochem class. And then I made projects that align to that. And these projects all connect together and show them how to apply it. And rather than giving them something they've seen before, we tend to look at novel types of questions. Specifically, we're looking at amylases, which is my research direction. And so we're exploring amylases from other organisms that haven't been characterized structurally and comparing them to known structures, and then trying to describe mechanism and function and differences. And so first couple of weeks, we're teaching them how to manage scientific data and searching the literature. And I frame this within 2 team-based projects. One that is, again, focused on, here's a set of data. What do you need to do to organize it? How do you keep a notebook in a way that we can do this? And then the second one, we're researching an awesome biochemist, and I specifically focus on those who you wouldn't normally have known about, specifically those from minoritized backgrounds or who are not the typical, you find them in every textbook scientist, to help them understand science is a struggle and that there are barriers. And that these 2 first projects are really about building community. And once you have those down, you can then begin the more in-depth and more content-driven types of projects, which are linked to the goals of the course and the learning objectives, such as modeling protein structure, predicting its function, and digging more into that, doing simulations and molecular dynamics, and ultimately doing drug design and docking and predicting what should inhibit this particular enzyme. And then their final exam is effectively a project where they have to work individually to design their own disease. And so they go pick a protein, they make a mutation in it virtually, and then they have to take it all the way to metabolism and explain what would happen and provide preliminary evidence, much like they've done in these earlier sections. And they have to write it up sort of like you would the preliminary data and background and significance and justification for a grant, and ultimately proposing experiments that they would do if they were in a lab, because this course does not have a lab associated with it. So the students are just in the lecture, and we can only talk about the theoretical aspects. And then something that I've worked on in a general chemistry example, and this is done with a team, was our department wanted to do something different with Gen Chem. So we were trying to convert our 20 to 25 sections of general chemistry lab with about 24 students per section into a more research or project-based type of situation. So we laid out our first semester lab was going to be project-based. We had well-defined goals of what the students needed to do, but we didn't tell them how to do it. And so they had to figure a lot of it out and think about controls and what to do, and learning how to develop hypotheses using a claim, evidence, and reasoning framework. And we taught them a little bit about techniques and communication. In the second semester is where we introduce a novel project, and our 2 projects are brewing beer and bio-inspired plastics, and that's worked out really well. We divide it into the training phase where they're learning how to do things and learning how to brew the beer and learning about the background and how to set up their experiments. And then they propose what they want to make their beer out of or what they want to make their plastic out of, and justify that why this is needed or what could be done with it. And they actually do that and present their final work. And so this has been hugely successful. We're putting about 500 to 600 students through this process every semester. And I do want to point out, again, we don't have any graduate students or teaching assistants. It's a faculty member in every lab space. So we've got the entire department had to buy into this project to get it to work, which can be a challenge sometimes. So when you're thinking about designing your cure, there are learning objectives and those goals and what you want the students to learn. But from a practical standpoint, you might also consider who are you teaching. This might affect the level in which you're trying to do. Who are your teachers? Is it just you versus a team of TAs versus an entire department? Scale can be different, 15 students versus 500 students. And also thinking about the professional skills that you want to lay in there and how they may influence what you're doing in your particular topics. So that ends my section, and I'll turn it back over to Jess and Ellis and continue from there.
Before we continue, there are 2 questions in the chat. And before I address them, I would like to let Dries talk a little bit about the cost of implementing a cure and how the Protein Society can potentially help you if you want to implement a cure.
Yeah, thanks so much, Betsy. So that question came through. You're welcome to look at a lengthier explanation in the Q&A, but in a nutshell, yes, absolutely requires resources. If you're fortunate enough to take the argument that this is a high impact practice that will retain students and We'll see them through the curriculum. I think that's an relatively easy sell, right? Like that's one of the things that I use with my administration is say, if we retain 2 more students, that pays for the course release that I need to do this well. And so oftentimes you can use that as leverage, particularly if there are funds available to it, right? Institutions are glad to have NSF dollars. NSF supports a lot of cures. I see that less through NIH and other mechanisms, but there are ways to develop and support those in a meaningful way. So if it's structured around, so 2 mechanisms I would suggest. One, Jess mentioned about structuring it around a fundamental question. If that's the case, then IUs is a good mechanism for that. If you're part of a community that naturally do some things, for example, I have colleagues who are involved in a genomics project together, that is a natural group of folks who are already together, then that would be a really nice mechanism or a really nice foundation for an RCN UBE proposal, where you're crowdsourcing through multiple folks within a network that support one another to try to achieve different aims. So yeah, I hope that answers some of that. Again, for more details, you can hop in the chat, in the Q&A, sorry.
So the next question in the chat is from Mary Grace, and she's wondering, are there any resources for biophysical, bioinorganic chemistry cures? She noticed that there are many for biochemistry, but she's specifically interested in biophysical chemistry.
I know people who teach them, but I don't know that they've published it yet, or have those resources out there. And I can get you in touch with them if you'd be interested.
Sorry, if I can quickly add on to that. I'm in a chemistry and biochemistry department, and I would say that there are a lot of folks who are doing stuff like this, and it's just not out, just as Chris said. So some of the chemistry side, the problem that the chemistry side has had is that they're doing really awesome stuff, and it's just been slow to getting out more publicly, at least in the spheres that I'm a part of. I haven't seen it come out as much as those on the biochemistry, life sciences side of things as much. They do exist. It requires some digging, and Jake Chemet is a good place to start. And again, I would say if you have a colleague who's doing something cool, just start talking and start coming up with some ideas. I'll share later on in the curiosity part. I'll share with what we did for bioanalytical, and I'll try to tie back to that about how we might springboard off of that. That was more an authentic inquiry lab, and you could imagine how you might parlay that into a cure as maybe a softer stepping stone into a cure.
Yeah, if I can address the issue too. Later on in the webinar, we're going to talk about, in essence, pairing cure semesters up through the curriculum. And that lends itself to a nice segue from sort of introductory chemistry to biochemistry or molecular biology to biophysics. And so there's some natural ways that those things can evolve.
Okay, we have some other questions in the chat, but I think in the best interest of time, we can perhaps move to the next speaker.
All right. So thanks very much. Let me just get my screen up. All right, so I am the first speaker. I'm Kevin Callahan from St. John Fisher University in Rochester, New York. And I'm kicking off part 2, which is optimizing student outcomes in cures, right? So obviously this group of panelists are huge advocates of implementing cures and all the benefits for the students, but we're always thinking about how we can improve on it, how we can, make it better for the students, make it better for the faculty. And one of the aspects that me and some of the other colleagues have been focused on is, we have all these distinct features of cures that have been laid out really nicely today. But one of the aspects that we spent a lot of time talking about or thinking about is collaboration, right? And what collaboration means. And if we asked our students what collaboration means, they would probably say, well, I collaborate with my lab partner, and when I need help, I ask my teacher. And they would not be wrong, right? That is collaboration. But what is the collaboration that, when we were in graduate school or as a postdoc or near even now as a faculty, what is the level of collaboration that we have experienced, right? And we know, as I've put up here, that collaboration has this huge benefit, right? It was great when I was in graduate school and is great now. It increases student performance and motivation. But again, how can we model that higher level collaboration that we've all experienced to a student in a classroom, in a CURE, right? And so the way that we've approached this is to model what we call external collaborations, right? And so to take this collaboration beyond the great collaboration that does exist in the classroom, but take it beyond that. So what does this look like? So again, I'm going to be using this phrase called external collaborations, and I'm going to describe for it what it looks like now. All right, so here I am in upstate New York, in Rochester, New York, which is unfortunately cold again today, but I have students who work in the lab, right? And so I implement the malate dehydrogenase in my biochemistry lab CURE, and they work on a hypothesis and they perform site-directed mutagenesis as it's been described. But what we try to do is during the course of the semester, as they are working independently, we wanted to bring in an external collaborator, right? And so initially what we did was we would bring in faculty members, all right? Faculty members from this MCC community who have experience with malate dehydrogenase and experience in implementing a CURE to interact with my students, right? And so we started this in about 2017, where we would bring in faculty. I would bring in faculty from different institutions into my classroom. And obviously we were doing this virtually, right? We were doing Zooms, you know, before they were even cool back in 2017. And so what would this actually look like from a practical standpoint in our classroom? Okay. And so we set up a large scale study. So this was part of an NSF funded grant. And we were trying to model collaboration and see if there were benefits from this, right? And so I will briefly go over this, and I think and fairly quickly help you understand what we have. So we had 3 groups, okay? We had, as you can see here, we had a no CURE group, a CURE group, and then this, as I described earlier, an external collaboration. And all of them had common elements, okay? Whether you're doing a CURE or not a CURE, right? You introduce a project. There is some collaboration with your lab partner. You perform data and experiments, evaluate conclusions, right? So that's standard across all, right? Now, we have been talking about what CUREs have that your more traditional labs do not have, is that our CURE students had to read literature and develop novel hypotheses, just as the students in the external collaboration group did. Okay? But what differentiated this external collaboration group was this interaction with faculty from the outside institution, right? So we would set this up where they would interact with our students twice, once during the proposal phase, where they would present their proposal, not just to me, but to an external collaborator. And then at the end, when they were, you know, they had interrogated their hypothesis, they had performed experiments, and now they were going to show the results. They showed them not only to myself, but also to this external collaborator, right? And what I want to point out is that this was done over multi-years across multiple institutions, right? So we had PUIs, we had R1s, we had community colleges, we had upper level biochemistry, we had more introductory chemistry levels, right? So we had a wide, diverse swath of students and faculty and institutions implementing these external CUREs and the control groups as well, right? And again, I'm not going to show you a lot of data about it, but the kind of top lines is that we saw that in this external collaborating group that student gains in experimental design as measured by the EDAT. And if you're not familiar with the EDAT, okay, it's something that was given pre and post, as all the surveys I'm about to describe were, to our students to, again, evaluate different elements of experimental design. And we saw marked and significant improvements in that. The students had perceived benefits, right? Again, surveys pre and post the CURE in different aspects, right? Specifically communication, ability to understand primary literature, learning to work independently, interpreting results, right? And it's probably not a surprise if you have to communicate to someone, a faculty at a different institution, probably something you've never done before, right? You're going to feel good about that. You're going to feel like I grew as a student during that time. And we certainly saw that in a quantitative way, right? And then also the students saw an increased importance in overall STEM fields, right? When they start to see that a project is not just occurring at my institution at St. John Fisher, but across the country, and that we're all working together and collaborating, they start to see, wow, you know, this is really relevant. This is really important, okay? And so if you want more details and more of the data, so we recently published this in CBE Life Sciences. And so the references below. The last thing, you know, what's next, right? Again, we took CUREs and we threw on external collaborations, and we wanted to see how we can make it better. One aspect we're doing is what parts of that external collaboration are key to getting this independence, this motivation for our students, right? How frequently should the meetings be? What should these meetings look like? Is it better for the collaborator to be in the same field or a complementary field? So that's when we're just thinking about external collaboration and how we can really make that part better. But there's more to collaboration, right? And I am going to turn this over to my friend and colleague, Betsy Martinez, who has taken collaboration, not just from the faculty side, but to the student-to-student side. So I am happy to introduce Betsy right now.
Thank you, Kevin. Let me just get a minute here and share my screen. Okay, perfect. There we go. Hey, hi. So we have all been listening to how wonderful CUREs are and all the benefits that they have for students. And I will argue that the students are a very important part of the CUREs, but also CUREs have many benefits for faculty as well. And one of those benefits for faculty is collaboration and also the networking. So Kevin was explaining how we got a collaboration going between students and faculty at a different institution. And after working on that project, we started to wonder what happens or what will happen if we have students collaborating with other students. So basically a student-to-student collaboration. And in order to investigate that, we decided to take advantage of our network. We are part of the malate dehydrogenase CURE community that has many different institutions across the country. So the way we approach this was by establishing a student-to-student collaboration between a community college, and a primary undergraduate institution. And we did this for about 2 years. So it has been field tested for 2 years. And the students at the primarily undergraduate institution were taking an intermediate level biochemistry class. And the students at the community college were either taking introductory biology or they were taking a genetics course. And our goal when we were doing these activities was to provide guidelines for best practices, as well as to create a set of assignments that students could do to kind of get their perspectives on collaboration and what they gain from collaborating with other students in the same project. So we basically set it up, and we had students from the PUI talking to students from the community college at least twice during the semester. In addition to that, this collaboration allows students not only to share their thoughts on hypotheses and experimental design, but also to share reagents and strains. So in a minute, I will tell you exactly what we did and how we set this up. So as you can see here, during the very first stage of this collaboration, the students work on hypothesis development. And rather than talking directly to the instructors, they are talking to other students that are working on the same project, the same enzyme. And they review the literature independently. They do some bioinformatics analysis independently. And then they have the first consultation and collaboration meeting with the collaborators at a different institution. And what we expect them to do during this first meeting is, number one, get to know each other. Learn a little bit about each other and what you have in common, and then start talking about your hypotheses. How are they similar? How are they different? Provide some feedback. how is your hypothesis better, or how could it be improved, etc. They also share a formal proposal, because the students in these courses are writing grant proposals about their malate dehydrogenase projects. And that's the very first assignment, the very first meeting. Then after that, this usually happens during midterm. Then after that, the students go and do their own stuff. So at the community college, the students normally either work on side-directed mutagenesis projects, or they work on enzyme activity assays, versus at the PUI, the students are taking a biochemistry class. So mainly there, they are focused on protein purification, enzyme kinetics, enzyme activity assays. During this part is when the students also share materials. So as an example, we have had students from the PUI providing purified protein for students at the community college. And likewise, we have had students at the community college providing mutants that they have constructed for the students at the PUI to purify and test. So this goes on for the second part of the semester. And then at the end of the semester, the students communicate again, and they talk about their data. They talk about their challenges. They share all this information. And then we also provided them with guidelines for a reflection assignment, so they can, express their feelings and their thoughts about how the collaboration helped them be better scientists, or what they learned from this process. And we decided to assess this, or to get some information on what the students thought, because we have field tested this for 2 years. And what we learned was that students participating in this student-to-student collaboration, they really appreciate the improvement and the effect that it has in their communication skills. They feel more confident, and they feel better about communicating science. In addition to that, we learned that they are more careful planning their experiments and collecting data, because that is something that they have to report to their collaborator. And in addition to that, we also learned that the assignments and the guidelines that we provided them with to be able to set up the collaboration meetings and to be able to organize a research conversation were very helpful to them. So if you want more details, we are hoping to submit this to CourseSource in the near future. So hopefully sometime later this summer or early next fall, it will be out. So we have provided guidelines on how to set up a student-to-student collaboration and some ways to assess it. What we do know is that we were able to get some very insightful quotes from students about how they have enjoyed this experience, and you can see them. One of them see it as a way to be part of a scientific community, something they never had before, especially outside of their institution. In addition to that, some of them, because they have not taken too many science classes, they appreciate the perspective. Oh, I am a chemist, and now suddenly I'm learning all these biological things that are related to proteins. And overall, they think it's a really cool way to get to know different people that are studying the same thing and share common interests in science. So that's all I have.
Right. I think, Betsy, you're still sharing.
Yes, I will be out of here in a minute. There we go. Go ahead, Regina.
Hi, let me see if I can get us continue going here. Am I set there? Excellent. I would like to thank everyone for being here, spending some time with us, listening to us talk about how we think about sort of these opportunities for students. My name is Regina. I teach chemistry and biochemistry at Kalamazoo College. And I'm first going to start out by apologizing for my voice being raspy. This time of year, it always happens. But what I'm here to tell you about today is a little bit about how we have been approaching doing cures here at Kalamazoo College. We are a small liberal arts college in Southwest Michigan with a student body of about 1,400 students. And specifically in the chemistry and biochemistry department, we have about 40 majors or so a year. And so part of it is thinking about how do we get more of our majors engaged in research early on. And the reason for that is because, as we all well know, we have these opportunities for students called REUs. So these are these high quality undergraduate research experiences that foster curiosity, discovery, dissemination, and reflection in our students. A little bit of a fun fact, turns out we don't have that fun fact. Let me go back to this. Fun fact, the National Science Foundation began these REU programs in 1986. So for approximately or almost 40 years, we've been thinking about how to get undergraduate students to really engage and think about research. The reason we want to do that is because we know that they're very essential components in research. This was a slide that I kind of stole from Ellis from last year. Our research components usually have relevance in some topic. We engage students in scientific background searching. They have to develop hypotheses, all of the things that you've already heard that are sort of the hallmarks of research experiences already, and things that we try to incorporate into CUREs, all the way from students performing experiments, data analysis, and then presentations. So we know that these REU programs will do that for students. The drawback is that REU programs tend to be selective and they impact just a few students. So it got us thinking, and at least the community of CUREs, as you discovered, is really fairly recent. Since 2014 is when a lot of the work that we're talking about sort of was dubbed and coined CUREs. I just started thinking if we could all imagine if teaching all of our labs could help students develop research skills by engaging them in solving real life problems, or at least letting them feel like they're solving real life problems, as a reason that we teach all of those experimental techniques and skills that we expose students to in our teaching labs. So for that reason, CUREs, I think, is a really good way for us to do that because it gets away from the selectivity that we find with a lot of the research experiences, the REUs. So we have to really think about what CUREs is, and you've already heard several ways of thinking about CUREs. They're learning experiences. They engage the entire class in addressing research questions. And it also helps them think about outcomes for some problems and their outcomes, and how do we really engage students in thinking about things that are helpful. So the characteristics of CUREs is that they have an element of discovery, they possess broadly relevant topics, they rely on an iterative process, so students have to do things more than once. They encourage a high level of collaboration, as you've already heard. And they also support scientific practices and processes, not the simple, solely learned, one and done skills that we often do in our teaching labs with students. So if you think about REUs and then think about all the things you've heard about CUREs, you can really see how these things overlay, or the two ideas overlay nicely, given this framework image that I have here, right? In the CUREs, you have these guided questions. They learn experimental techniques. We can develop questions and write protocols. We can help students design experiments. They have to carry out the experiments. In the CUREs is very autonomous. We have to develop open lab times for the students, and they get to collect and analyze data. And then we also include things like poster presentations, oral presentations, and formal paper writing. So the two things really overlay, and where REUs impact few, the CUREs has the potential of impacting many. So currently at Kalamazoo College, most of our labs, at least in the chemistry department, I will speak for my department, chemistry and biochemistry department, most of our labs work out of a lab manual. They have a canned series of experiments that literally walk students through select series of techniques. And there's no room for time for correcting or troubleshooting. Part of what I often hear with students out of those labs is, yeah, I had lab today, nothing worked. And they walk away with the experience thinking nothing works. So more recently, several of us in the department have been having these conversations and planning and thinking about how can we develop CUREs for our classes. And I've been teaching a medicinal chemistry class in really what ends up being a CUREs format since 2008 without really calling it a CUREs. We're now working on other labs in our department And so we're designing labs for the purpose of solving societal problems, some big societal problem, for example, antibiotic resistance. We give students some basic background training in lab. So they still have to learn spectroscopy. They still need to learn how to calculate concentrations of molecules in a solution, but we give them those techniques with the backdrop of using them to solve the problems that we're thinking about. And then we really allow and give time for students to make mistakes, and they have to do it over. And I'm going to do spoiler alert. Students don't really like the redoing of things in most days, even though a lot of them do enjoy the fact that they can fix the errors that they made from one week to another. So what we have at Kalamazoo College currently is a series of what we're calling these horizontal cures. And horizontal cures then are single course based. Some of them could happen in the first year, second year, third year, or fourth year of the students being at Kalamazoo College. They're one semester. We teach in 10-week terms here. So they're terms, not in semester, but these horizontal cures can be in one term or one semester, sort of sprinkled in across the curriculum. They could be the whole class. So for example, our new biochemistry class for our majors is a whole class cures, but it's a horizontal cure because the students only work on it in the biochemistry class. Or these cures that are horizontal could be modular. My colleague in the organic chemistry has developed a modular cure for the second year organic chemistry class where the students do a one-pot synthesis and then they test it. So these horizontal cures can do these things. The disadvantage is that it can be isolated, a one-off, and students feel like they did that one thing and they're done. We know that that's not how we really do research. But the advantages are that it exposes many students to research experiences, it connects real-life problems to concepts learned in class, and it fosters collaboration and deeper learning, something that is hard to do when we're getting them in and out of like one topic, and then we just jump into the next. So horizontal cures sort of have all of the makings that you've already heard of cures. The relevance or the who cares really is based on the topic in a given course, because remember, horizontal is from course to course to course, they change. And then in the case of the three questions that we ask, the three questions that are here, what do I need to know? How do we measure? We know that we have to create those things in the cures, but the nice thing about these cures is that it allows students to explore and develop research skills. So in the horizontal cures, again, it happens in one course. Recently, I've been thinking about and working on what I'm now dubbing and calling vertical cures. How do we think about infusing cures all the way from the first year students arriving on campus, all the way to when they graduate? And so these vertical cures can actually bleed into the 4 years at the college, students really thinking like a scientist. There's a problem to solve. And in all of the levels of courses that I do from first year all the way to senior year, we're learning all of the scientific tools to solve that problem. The advantages are, in addition to all of the things that we see with the horizontal cures, is that it really helps teach students how multidisciplinary research is. So these vertical cures would have multiple courses across the curriculum, multiple terms for us, or semesters if you're working in a semester system, multi-institution or disciplines, even though we have not started doing that here at K. We're sort of focused on the chemistry and biochemistry program at the moment. It's a whole class, or it could be modular. Depending on what we decide to study, we could incorporate them differently throughout the 4 years. And they can be more collaborative, less isolating. The ideas that we have is to have students that are doing senior level courses, a little bit like what Betsy was talking about, talk to the students in the first year courses. Because for us, the relevance then becomes one recurring topic. Let's pick one topic that's going to be the topic that they're going to think about for 4 years as they learn all of the different all of the different tools from first year to senior year. If we think about the 3 questions, what do we need to measure? That will vary from course to course, sort of like the tools that we're going to use. What will change the probe, that will also, to probe in the system, will also change from course to course. And how will we know we will build, that will actually build in from course to course as we help the students think about what they're learning from one year to the next. The beauty of the vertical cures, I think, will allow students to explore and develop skills in a continuing process, much like what we actually do in research. Again, this is theoretical for us right now. We're really thinking creatively for the chemistry curriculum. I'm missing a slide, there it is. For the chemistry curriculum at the moment, we're working on introducing this in our introductory chemistry courses, one of which I teach a year, the organic chemistry course, biochemistry, which I teach, I'm a biochemist here. I also teach a medicinal chemistry course, which is a 4th year level course. And then my colleague, who's been my partner in crime in a lot of this, teaches a natural products synthesis class. And so we are together thinking about how do we infuse this thinking in our students beginning in their 1st year all the way up to their senior year. And so with that, I would like to just acknowledge the CURES community for taking me in a few years back, and my organic chemist colleague, Dr. Dwight Williams, who teaches here with me in the chemistry department. And I thank you, and if you have questions, we can answer later. Chris, I think I'm passing it on to you again, right?
Yeah, I believe so. Thanks, Regina. So I'm going to build on this idea of collaboration within and between CURES and talk about how we can use it, work with CURES to share faculty expertise and facilities and all work together to succeed in the end. So the big idea is that collaboration is a major skill and a resource in science. If I don't have a piece of equipment, but I know someone who does, I can still make success by working with them and continuing with them as a collaborator. And few schools have all the instrumentation or expertise to completely characterize a protein or a particular biomolecule. And especially at undergraduate levels, this can be the access to instrumentation and courses can be limited depending on where you are. And CURES and faculty working together is an opportunity to combine resources to enhance undergraduate student access to instrumentation that may not be available. And we all know that collaboration is important. Teamwork is important. Whether you are an academic or whether you're in industry or wherever, you got to know how to work in a team and how to communicate and how to work interdependently. And so this is a professional skill that we can show students how to do. And this can fill in the gaps to complete the story. You know, a new poster, a new project, a new manuscript, get those things done and support our scholarly growth as academics, especially at teaching intensive institutions. So I love collaborating. I do it quite often. And give me a moment. I'm gonna stop sharing, try to come back at it. Okay. Okay, so awesome. Okay, so there are a couple different types of collaborations that can happen. There are data gathering collaborations and there are collaborations to complete a project. And so I'm going to talk a little bit about both here today. What I do here at JMU is I sometimes work within my own CURES to get collaborations to go. I've got my lecture and my lab course, which I've described a little bit and how they work together on starch degradation, and that informs my research lab. But also the bioplastic project and Gen Chem, they are also working together, and we are working together to make forward progress on different aspects. But we've also turned this into an outreach project, and now I work with elementary schoolers at a local elementary school, and we've gone in several times, and they're actually helping us look at degradation of different plastics that we've generated in the lab, and they're learning about professionals being scientists, and we're going in and showing them that everyone can do science and trying to foster their growth as scientists even at a young age, so that hopefully they stay and persist and become the future scientists as we move forward. Now, in addition to sort of these local types of collaborations, there's also opportunities for data gathering collaborations where you work with other institutions, like we've heard from Betsy and Kevin, to organize and plan and work together. But what I'm going to be doing in this type of collaboration would be, I'll be collecting data for colleagues who may not have access to a particular piece of instrumentation, whether it's, say, circular dichroism or multi-angle light scattering or small angle X-ray scattering or other sort of biophysical techniques or biochemical techniques, working with them to design an experiment so that I collect the data for them, and then I work and give that data back to their students and work with their students to understand what they've got and connect it to what they've collected there locally. And there are a couple of things to think about when you're doing these types of collaborations. One would be the role of the students. Are they going to be passive? Are you going to engage them? How are you going to do that? Synchronizing the calendars and shipping of samples and getting all that to line up so that you not only can collect the data in time, but also have enough time to work with the students to understand and analyze those data, how you're going to share the data. Sometimes these files can be pretty big, and email won't let you share it that way. And again, the expectations of the students. What are they expected to do in this whole process, given that they don't have access to the instrument and they're not in person doing this type of data collection? So what I've been doing, and I've worked with Kevin, and in fact, we had a session this morning talking with his students, working at some of the data I collected here. So his student teams purified malate dehydrogenase, and then they shipped the samples to me, and I collected size exclusion, chromatography, multi-angle light scattering data on those particular samples. And we had the data, and I sent it back to them. In addition, I had recorded a video explaining, what the data were, what the technique was, and helping them think about what they had gotten back, and then gave them some guidance on what to do so that they could get started and understand what they had derived. And then met with Kevin and his students, and we talked through some of the data and how they could connect it to their overall project and their understanding. And it worked out really well. It was a lot of fun. And I'm looking forward to continuing this in the future. But this is another way that students now had access to a new piece of equipment that they didn't otherwise have access to enrich and fill out their experience that they were having within the cure. There's also opportunities to collaborate and finish a project, and these are a lot of fun because you can sort of take a lot of data and try to work with others to find out where the story can be completed and add on to that story that's already existing. And so I've been working with Ellis and helping him understand and how some of the mutations work. And so his student generated the parameter files. What I did is I ran his molecular dynamics simulations and his students' molecular dynamics simulations, and then basically provided the data back and provided a way for the student to analyze it in the form of a notebook they could use to go through their data and understand more about what the steps were in the process of doing it. And they've been able to generate some really cool data overall related to this topic. And so my role really was just providing access to the computers and then providing guidance and knowledge to the student and working with the student to make forward progress, somewhat like mentoring, but more like a collaborator would be in-house. And that's been a great experience to do. And doing this with other cures as well, where they've got data and then working with them to round out what needs to be finished in the end. So there are lots of benefits to doing collaboration, both inside your institution, between cures, and working with other institutions to get access to instrumentation. And you get to have conversations with peers and scientists from other institutions. You can expand the range of data that are collected. You can also establish protocols. Maybe once it's been done once within the community, there are others who have that same instrument. You can establish the standards that can be done so that you can even enhance the collaboration even further for multiple institutions. And you can establish data management and sharing guidelines because not everyone collects data the same way. And again, you're lowering barriers for faculty and students to succeed and learn. That's the goal of a CURE, to provide students with access they may not otherwise have. And so if we can keep lowering those barriers and make it a better experience for students, we're going to win in the end. So with that, I'm going to stop, and I think we're at a break point, but someone step in and let me know.
You're correct, Chris. We're going to take a little break to answer some questions. One of them came in about the grading and how that works for these classes, and how do we design rubrics that can be objective. So if there's someone who wants to take the lead, perhaps there are a couple answers that we could share.
I can say for me, when I'm looking at the rubric, I try to keep it pretty simple and understand what objectives I want, and then grade on a 0, 1, 2 scale. Can they do it? Are they almost there? Or did they not quite demonstrate that skill? And they give more feedback. So it's less about scoring and more about giving them the feedback and having them develop that competency for what they need to know.
Nice. Dan, do you want to add to that?
Yeah, thanks. I know that, oh boy, it's a blur. I can't remember. I think Ellis showed some rubrics. I'm going to show some rubrics. I think backward design is your best friend. I mean, so clearly outline what your goals are in that lab. If you're trying to assess everything and you're not teaching it, then it just becomes a headache for trying to wrestle all of that stuff. So I think having really clear objectives and making it abundantly clear to the students that that's what you're expecting, and then creating assignments and developing activities in the lab that specifically talk to those objectives, I think that's your best bet. I know it's not concrete. And by the way, there are lots of rubrics out there for labs, how folks do that. I would say don't reinvent the wheel. There's always something you can grab and then tweak from there. And sometimes it's things that I just have never even thought about aspects of it, right? Things that to include and things not to include, frankly. So yeah.
I'd agree about not reinventing the wheel. For instance, MCC's got some on their teaching component that you can grab some rubrics from there that we've been using in CUREs classes, and I'm sure others have those as well. So that might be a way to address that.
Can I jump in and because one of my colleagues has this cool way of assessing technical skills in a lab and helping to build technical skills. I think she calls it badges. Maybe you'd like to say a few words about it.
Yeah, that's another way to assess skills and do it very objectively. Either the student can demonstrate the skill or not. So that's another way where one-on-one you work with them to demonstrate some of their skills. That's more technical aspects, not so much overall looking at a CURE and whether or not the student is understanding the scientific process. So different ways for different types of things we're trying to assess. Absolutely. The other one maybe we could touch briefly on is there was a comment on what about students perhaps being a bit deflated if things don't work? How do we address that? Do we want early experiences in science to be positive, that is, they get something that works, or should we be allowing them to fail? We gave some comments in the question answer. You can look at those, but if anyone else wanted to comment on that, please.
Yeah, go ahead, Regina.
I was going to say really quickly about grading. I try not to do a point system for these because students get stuck on, I lost a point, and then they lose the whole reason they lost the point. So I do it more on a, you did it, there's a check plus kind of thing. And then we talk about when you didn't do it. And it becomes really apparent to them when their lab mates are not doing. So they really self-police sort of the doing and the learning as well, since it's really open-ended. So that's one. But the question about, what was that last part there, Jess? I'm blanking.
Oh, should we let students fail or not, they didn't get anything work that worked?
Since I was the one that made that comment, I mean, I hear that usually it's the first year students, you know, you put together an experiment, they do it, it doesn't work. They don't even understand that maybe parts of it worked, but it didn't. But to them, they didn't get the answer that Dr. Truss wanted, as opposed to, I got this answer, what does that mean? So I am a true believer in letting them fail. And because I don't grade it on a point system, the deflated nature of it is not usually there. We can talk about what they did wrong, how could they do it again? And in my 2 cures courses, they have to do it over because at the end they have to finish something. And again, we have 10 weeks. So I let them get as far as they can get in that time frame from the learning some techniques and getting some things done without the challenge of I failed. So I try to take the I failed piece out of it because usually they didn't fail. They just need to redo it. So.
Yeah. And it's also, as Regina's sort of implying and Jess implied, it's a teachable moment when students in my cures come up and say, this is what I got, is it right? My first response is, how much do you believe the data? How much do you? And it brings in this reproducibility, you know, and really getting students to think about what the data is telling them.
Mhm. Kevin, and then Dan, and then we'll move on to Dan's talk.
Yeah, I was just going to say really quickly. I mean, I find there's almost always something that you can find a success in then one of their experiments, right? Whether, you know, even if the gel didn't come out good or the activity assay didn't work perfectly, there's something that you can talk to them about that they grew from, or that, okay, you did this or you learned this, or what does this mean? So there's always something, and that I think if you dig deep enough, you can bring something out that they learned from it. So I'll just say that.
Yeah, thanks. So 2 things. I guess the first is the so I would say that if you're thinking about designing a rubric, again, I would say ask what your objective is. For me in my classroom, it's based on the process, right? So if your main objective is, can you be a scientist? And Lord knows we failed probably more frequently than we succeed in the lab. Then if it's process-based, then that's what you're trying to teach, and that's what you should be assessing, right? In terms of the failure, I'll share that I think this is, and this is not an accusation of the person who asked the question, it's just an observation that chemistry has a real, I don't know if I'd say problem, but there's an inertia behind. There is a certain set of skills that they need to be able to do in order to move past. And it's really hard to move that inertia in a chemistry department or in the field for some particular folks, right? And so there's just a sense that that is the case. And granted, in some cases, it is a real safety concern, right? Like legitimately, I get that. But I would say that the trade-off is if folks are doing routine things that are predictable and still not getting good results, and then they're getting deflated and they don't see the purpose of it, the trade-off is doing that versus something that, you know what, it's okay because I don't know the answer either. That's why we're doing a cure, because there is no predetermined answer. And so how do we know if this is good data or bad data, and what do other folks get? It is intrinsically collaborative when you're starting to talk with other groups and trying to triangulate where things went wrong and all those kinds of things. So to me, it's the trade-off is worth it. But
Can I as a chemist say, Dan, that's literally why we're thinking about first year, second year, like the continuum, right? For exactly.
Nice. And remember, FAIL is an acronym, first attempt in learning.
I love it. I love it.
All right, I'll turn it over to Dan. He's going to talk to us about hypothesis development and curiosity.
That is a beautiful segue, by the way. I love the FAIL acronym. Thanks, Jess. I do want to start by sharing that I am giving this presentation on the ancestral lands of the Onaga Nation, the Oneida Nation, the Susquehannock Nation, and the people of the Standing Stone, all of whom are part of the Haudenosaunee Alliance. And I do want to honor and acknowledge the folks who have stewarded these lands over the years, including past and current generations, and then of course the future stewards of the lands. And I am working with Juniata College to try to disrupt this legacy of occupation of these lands. If we're thinking about helping students develop as scientists, I think we need to have some appreciation and motivation. And this speaks directly to some of the things we just talked about in the Q&A, right? What motivates our students? Why are we ourselves motivated? And so let's take a really brief tour around motivational theory. Okay, I'll try to keep this as light and quick as possible. There's an excellent review from Richard Ryan and Edward Betsy who talked about intrinsic and extrinsic motivation from a macro theory of motivation. I'll get into that macro theory in a little bit, the self-determination theory, but we can think of this as on a continuum, and I don't think this is going to be much of a surprise, but I think that the quotes are helpful to frame this, okay? So the worst case scenario is, I just need to get through this lab, right? That is a motivation. That is not what, I think it's accurate to say that that's not what we hope to achieve. Then there's all this extrinsic motivation, which is not that they themselves enjoy it, but rather that there's utility in this beyond the self, right? So we can talk about external and interjected regulation. These are what are called controlled motivations, meaning that I don't control it, but that other sources outside of me control that perception that I have. So for example, I'll do what it takes to get a good grade in the course, right? Or I don't want to be embarrassed, right? So this is kind of edging closer to the personal, in this case, the kind of the shame aspect, if you will, of it. And then we could talk about autonomous motivation, which is still external. It's coming from outside the person, but that there's still some sort of meaning to them, right? So what I'm learning will help me in my future, or this means a lot to me. There's personal relevance there. The best, I think, that I would at least want my students to do is to have an intrinsic motivation. It's fun. I just want to do it because it's fun, right? And that's what we're talking about when we think about intrinsic motivation. It is a lofty ideal to achieve, but I think it's one worth pursuing. So if we pull from a bunch of different theoretical frameworks for motivation, Betsy and Ryan came up with this self-determination theory. And the idea is that they said that a person can be maximally motivated if three psychological needs are met. The first is that they have to feel like they're competent in what they're being asked to do. The second is that they have to feel a valued part of that community. And the third is that they have to feel that they have some sort of choice. And I think we can all probably relate to that. I can tell you I do my best work on committees that I join because I have a horse in the race, so to speak, as opposed to something that I've been assigned or dragooned into. And so this is what ideally, if we want to foster maximal motivation, is something that hits the confluence of all three of those. I feel like I have a choice. I feel like I'm a part of this community, and I feel like I'm able to do the stuff that I'm being asked to do. Okay. And that might not necessarily mean perfection. It just means that I'm able to perform those acts and make progress, as little progress as that might be at times. The problem is we scientists often focus on the competence, right? This is kind of what one of those questions came at, which is, but aren't there skills that our students need? And don't we have to give them fundamentals before they do other things? And so I think we have a tendency to focus on lab skills. And as an example of this, I love this quote from Ray Bradbury's Fahrenheit 451. If you're not familiar with it, I don't know if it's a satire or allegory about preserving ignorance by burning books. And people can control the information to control the individuals. And so this quote reads, "Cram them full of non-combustible data, chock them so damned full of facts that they feel stuffed, but absolutely brilliant with information. And then they'll feel their thinking. They'll get a sense of motion without motion, and they'll be happy because facts of that sort don't change." And this resonates with me because I think oftentimes I feel like I'm telling my students an awful lot of stuff. They feel like they're learning a lot of stuff. And then when we're asking them to apply stuff in the lab or the classroom, that it just starts to fizzle. And so, right, we want to make sure that we're not giving them a sense of motion without moving, but motion that they are in fact moving. So, competence is great and it's important. Yes, it's important. But when we ignore those feelings of relatedness or belonging and choice, then we run the risk of having that enthusiasm in the lab kind of wither on the vine or wither on the stem, so to speak. And we don't want that to happen, obviously, right? Particularly when that withering happens on to particular groups of students in our classrooms and laboratories. So intriguingly, these same three ideas, concepts, were interwoven in a construct of science identity. So this was pioneered by Heidi Carlone and Angela Johnson. And what they were looking at was identity theory, rooted in identity theory by James Gee, who was a sociologist. And what they found was by surveying students and asking, how do you feel like you are a scientist? They came up with 3 key issues. One, perhaps unsurprisingly, is competence, feeling like they have knowledge and the ability to do things, knowledge of the science content, that they have some ability to perform that science. That might be doing calculations or doing things at the bench, and that they're being recognized as a scientist by multiple stakeholders. That might be their peers, it might be themselves, it might be their instructor. An important overlay to this, and one worth noting, is that Carlone and Johnson also recognized that because science identity is a social construct, that other parts of that social identity creep into and intersect with science identity. And so, for example, when certain groups of students hear stereotypes that whether they agree with it or not, subconsciously they adopt that mentality that perhaps I'm not supposed to be doing these things, right? That's stereotype threat. And so stereotype threat can whittle away at one's feelings of being competent. Feeling that somebody doesn't belong here, that somehow by divine intervention, they're a part of this, that they're doing this particular activity. Imposter syndrome can creep into the feelings of being able to perform in the lab. And then either bias of the instructors or of their peers can impede their feelings of being recognized as a legitimate bona fide member of a scientific community. So these are important aspects to think about. Now, the great thing is that CUREs can try to counteract a bunch of these things, right? By being alongside students, doing science experiments along with them, we can be there to give them a pat on the back, to say that they've got the knowledge that makes them a scientist, to make them say, hey, you are actually doing this particular experiment, and to say, you know what, you failed, and guess what? Science is about failure. You've earned your badge in failure, so now let's try to move past it. How do we do that? And so CUREs are a great opportunity for that. Okay, so if we want to develop and support our students' our students' science identity, and if this is understood as performing as, being competent as, and being identified as a scientist, then we need to ask ourselves what makes a good scientist. So I'm going to ask you all to take a few seconds here, jot something down on your own, not in the chat or the Q&A. We'll have time for that in a minute, but take a few seconds and think of yourself not as an educator, if you are an educator, or as an instructor, but rather as a practicing scientist. So what assets do people bring to make them a good scientist at the bench? So think about that for a little bit. Once you have your answers, you can navigate to this website and drop them in, and we'll see a word cloud start to pop up shortly. Great, go ahead and drop those in. Yeah, this is great. Awesome. So much of this, right, is being thoughtful, being mindful, talking with other folks, being patient with oneself. I love that, right? Being persistent. It's less about intellectualism or conceptual knowledge, or I mean, obviously there's some technical skill to it, but really it's about other things beyond just being lab hands, right? Even though oftentimes we think of lab hands as being the critical part of being a good scientist. Awesome. Feel free to keep dumping those in. I'll pull that word cloud out and post that in our resources at the conclusion of today. So some of the things that I came up with are the things that y'all came up with as well, right? So, oops. Let's bring back here. Okay. And so right, not afraid to fail. We talked about that, right? That came up in some of the language that came up here. Good lab hands, being curious, collaborative, analytical. So all kinds of different things that come into this. And so perhaps you were accused by the section of talking about curiosity, but absolutely, right? Scientists need to be curious. And so this is a standard thing that we see, right? Early on, that our students see early on about the scientific process. And yet it's not often represented this way. So we think about making observations. From those observations, we think of interesting questions. We're creative, right? Some folks put that in. From those questions, we can formulate a hypothesis, a clear statement that's testable and verifiable. We can develop predictions, testable predictions, generate data, refine that. And after several iterations of that, we can then develop general theories and kick this cycle all off again. The problem is oftentimes in our labs, we don't see that closed loop. And the nice thing about CUREs is that we do close this loop and make it a little more authentic to the scientific process. And in fact, I would say many of our labs, in fact, start at the test hypothesis. And a hypothesis might have been already pre-written for them in a lab manual. And they're really collecting data and focusing on analyzing results. Now, analyzing results is really important, obviously, but it's not the only part of scientific process. And if we want folks to feel like they're a scientist, which by the way has to happen early on because folks will decide within the first year or two, some would even say within the first 6 weeks of a semester, whether they're a scientist or not. If we want folks to stay in the sciences and persist in the science and the sciences, then this is a great way to do it, is to introduce them to this feeling that they're being a part of the scientific enterprise. So, all right, so how do we do this? Well, I would also argue that even though we often start at this testing hypothesis for what are called cookbook labs, right? That even some cures can be this way. And what I mean by that is if a cure is rooted in a predetermined question that's funded by an external source, sometimes that can limit the ability to develop interesting questions, right? Or at least there's a superficial imposition on how we can get at that. So, and so we still need to be careful and thoughtful about how do we develop curiosity in our students, because it might be so easy to just rush for data collection. So there are a bunch of different ways we can incorporate curiosity in a lab. There are different ways we can run instructional labs. This is a really nice framework from Lisa Corwin's paper. This was a summary of a meeting report several years ago, but it talks about this kind of continuum and various aspects of it. It's an excellent paper. I encourage you to read it if you're not familiar with it already. And we can think about this as a continuum from less independent, more given to students to a more independent hypothesis-driven side of things. And we can think about that as being from a more limited scientific process to a more complete scientific process on that continuum. And so the idea then is really what we want is to foster students' independence. Now, I teach question writing in my class all the time. We'll maybe talk briefly about that later on here. And when I ask my students, what questions do you have? Even the brightest of my students come to me and say, I know I have questions. I have no idea what they are. And that just stabs me in the heart a little bit, because I think what more demoralizing, unacademic, unscientific behavior than to say, I can't articulate my question. And so if we're going to teach curiosity, I would say that we have to think of a different question first, which is, how do students learn to stop being curious? And I'm not saying that they just become incurious. I think they actually are actively taught not to be curious anymore. So if you could just now drop in the Q&A some of your thoughts, I think Q&A is probably the best place to put these. How do students stop being curious? What teaches them to stop being curious? Grades, interesting. Okay. I'll call them out as they're being dropped in. I don't know if you're able to toggle back and forth, but yep, grade focused. Isn't that interesting that having a grade keeps you from being curious? Yeah, the most curious students are often told to quiet down to make room for others. Good. By the way, we should be thoughtful about who's training them to be grade focused. If you're not catching my indirect shot, I would say that we have a shared responsibility in that, right? Sorry, for those who can't or who are looking for the link, this is actually just in the Q&A. So if you go to your Moodle, or sorry, your Zoom window, you'll see it at the bottom. There should be a link to the Q&A. High stakes, good. Yeah, so I would say, right, there's social pressures. You don't want to look kind of teachers pettish early on, right, in grade school. There are issues of, I don't want to take time away from class. I don't want to interrupt my instructor. I don't want to look stupid in front of the instructor or in front of my peers. Right, feeling embarrassed. Yeah, exactly. Especially after what they think is, I can't tell you how many times people say, right, I think I have a stupid question. And it's almost like they're always apologetic for asking a question. And so I think it's really important for us to think about that. How are we dissuading students? And that includes instructors. When we are giving the appearance of a rushed lecture, for example, we are sending inadvertently, perhaps, hopefully, sending a message that we don't have time for questions. We have content to cover. We don't have time for questions. And then where does that fall, right? And so it's an important thing to think about. I'll give you a reference later on for some ideas of things to think about. But I will tell you that in my classroom, I explicitly ask my students to develop questions, and we get practice doing that, and they have a rubric to grade them on how well their questions are being asked. And so, you know, so that's in my classroom. Before a lab, we have a natural way of doing that, and that's developing hypotheses and getting practice in developing good, strong hypotheses. In fact, I would share, even from Juniata's perspective, we did an internal audit, or I should say an assessment, last year, and found that the weakest point of our students that they had in their coursework and in their laboratory work was the ability to generate a hypothesis. So it's common in a lot of places. So if we want to get students to ask questions, we talked about all these places where these different ways that impede our students' ability to ask questions. Then I think we need to create a safe spot for them, a safe environment for them to do so. So one helpful framework for this is understanding something about mindset. And so if you're not familiar with it, this is the work of Carol Dweck. She defines two particular mindsets. So the first is a fixed mindset. Those with a fixed mindset believe that intelligence is, that they're born with intelligence, that it's a natural gift, that it's unmalleable, it can't be grown. And because of that, a lot of those folks build their identity around their intelligence or lack thereof, frankly. And so this leads to people putting themselves in a protective bubble to keep them from their ignorance being exposed. So what does that mean? Well, it means that they avoid challenges because that's a chance to erode at that intellectualism, at that brilliance. They tend to give up easily when faced with obstacles, or say that the effort is stupid, right? So they say that the effort, it's not worth my time, my effort. I just want to move on with this and get the right answer. They often do not receive criticism well. They see that as a personal indictment of their character, of their intelligence, or they may be frustrated when being asked a question back, for example. They may be frustrated that they're being put in a position to start asking questions. And they feel threatened by the success of others, because if others are moving and they then are not, they're failing to live up to this intellectual ability that they believe they were born with. So that's a fixed mindset. And what I think we need to develop is a growth mindset and be really explicit about it. Those who have a growth mindset understand the brain as being pliable. We know about neuroplasticity, right? We can get brain changes to happen even in adulthood. And so these are folks who believe that the brain, to use a poor analogy, is a muscle, in the sense that you can work at it and build strength from it, right? So these folks who have a growth mindset understand challenges as something to embrace, that they're learning opportunities. They persist in the face of setbacks. They see effort as a path to mastery, a way of getting better at what they're supposed to be doing. And they see criticism as developmental, as formative. And, you know, when they see others being successful, they kind of glom onto that and ask, well, how are you successful? And how can I do that too? And good for you. And, you know, those kinds of aspects. And I think right? All of this, what that means is that rather than being predefined by your intelligence, you in fact have some sort of level of more free will ascribed to you, that your future is somewhat in your control in the sense of being able to grow and expand. And that's kind of the environment we should hopefully try to create. So that is that we need to create an environment that supports failure and criticism, an environment that helps folks learn from their peers, an environment that has iteration and availability to fail and get better. And this is naturally embedded within CUREs, right? And so I would say not just that, but even the instructor's attitude, peers' attitude, trying to remove fear or intimidation or power structures can go a long way to fostering that growth mindset. In the interest of time, I want to make sure we do have time for some questions. So I'm going to kind of fly through a few slides here. I will say that for reasons I won't go into, we ended up using, when we redesigned our biochemistry lab, bioanalytical chemistry lab, we used an authentic inquiry model. So it's not a full CURE, but it's not traditional lab. And the idea was this was a 200 level lab of anywhere from 24 to 48 students, 1 to 2 sections. The lab is filled with sophomores to seniors, majors, non-majors, health professions, whatever, a large group of different folks. And what our objective, our overarching learning goal was to have students come out of that lab feeling like a bona fide scientist, and that would be a gain for us. And so we wanted students to take control of their education and have some level of choice to the conception of a hypothesis, a scientific idea, all the way through disseminating their work with their peers. And so the way we did this is written up in JChem Ed, by the way, in a January 22 issue. The way we did this was to start with highly structured activities that they've seen before, and then to start chipping away at the structure to kind of wean them off of structure and get them into independence. By being a part of a team, they're naturally getting some sense of relatedness. This includes regular feedback of themselves and their peers. And then by virtue of doing a lab, they're showing signs of competence, and together, hopefully this would lead to increased self-efficacy. And so again, without going into too much detail, right, our objective is to get that bird to fly out of the nest, and doing that by weaning structure away and fostering independence and self-confidence. And so we start with a process-oriented guided inquiry lab sheet, learning sheet on just data analysis, just kind of straight up the mechanics of that, and thinking about standard curves and those mechanical aspects. And then we have them do a Beer's Law experiment where we pull away some of the structures. So we'll just say, here's your standard, here's your unknown, go find the concentration. So that might seem scary at first, but they usually have somebody in a group has enough insight to say, well, okay, we need to know wavelength, and we'll give them a spec. So, okay, well, how do we measure it? And then it talks about, well, how do you know? And what color is it? Oh, this thing has a certain color to it. And then we talk about absorption spectrum. So this is all kind of through a Socratic process of getting them to that. Yes, it's time intensive, but yes, they get a lot out of the process and start thinking more like a scientist rather than a pair of hands with not much of an idea of what they're doing and why they might be doing it. And so eventually they get to learn about why you choose the range of standards that you use and kind of that experimental procedure. Then we give them a protocol that's pretty bare bones and an unknown, and ask them to basically adapt that protocol, customize that protocol to their analyte. They get, by the way, the Beer's Law experiment, they get 2 weeks because it's a lot of iteration and talking through experimental design. This protocol development is 3 weeks for a lot of failure and iteration. The first week is really rough. The second week they come into lab totally ready to go. Even if the data is not perfect, at least their design is pretty straightforward. And then at the end of that particular module, they present their protocol to another group. And that group picks up with that protocol and designs their own experiment with several rounds of iteration. And then that group presents their work to the science community. So for example, we had an opiate ELISA where we had one group of students wanted to know if you could use popular detox methods they could find on the internet to beat a test. And so you can use synthetic opium, not that you would give that to students, obviously, but there are ways of doing this experiment in a ELISA format that's safe. they also said, you know, I know that there's opioids in poppy seeds. Let me see how much I can consume and then see if we can detox using that way, right? So it was really, these were all ideas generating from the individuals, and that sense of autonomy, that sense of discovery led to really productive outcomes. So just very quickly, we did an assessment asking students to compare their progress on meeting these course outcomes from this lab versus other chemistry labs. And two of the biggest gains were their ability to propose a research question and their ability to develop an experimental approach. Okay, so very briefly, I guess, we can talk about then, well, how do you do this? How do you foster the development of hypotheses and curiosities in the lab? If you've ever tried to ask students to do this, you'll find that they struggle tremendously with it, right? And so we can take advantage of backward design. I know Ellis mentioned this before, and that is articulate your learning goals. So maybe we want to say by the end of this laboratory course, students will be able to develop a testable and falsifiable hypothesis that emerges from existing work and contributes new knowledge to the field. So if that's what our goal is, then we can parse that out into discrete items and then parse those into different levels to say, talk about proficiency at each of those levels. And then from that, we can then build activities in our lab for how do we foster, in what ways do we teach students how to develop a hypothesis that's rooted in existing work, right? Or that contributes new knowledge. Oftentimes it doesn't. But we can be intentional about this, more intentional about this. And so if we do this and we develop those activities, then by the end of that, hopefully we will have taught students how to write a hypothesis that is falsifiable and testable, that is emerging from existing work and that contributes new knowledge to the field. A bunch of the great, wonderful folks on this webinar published an article in Course Source talking about this very aspect. How do you foster hypothesis development in CUREs? I highly encourage you to check this out. You can see this mind map on the right that talks about the idea. The idea is that you triangulate kind of bioinformatics tools, structural visualization tools, existing literature and content knowledge to develop some sort of big idea from which ideas and hypotheses can flow. And that process happens through formative feedback with peers, with instructors. They can make predictions and design an experimental approach. And then that together could be presented through an oral presentation or a visual presentation or in a written presentation like a proposal. The other wonderful thing that these folks put together for you are a bunch of rubrics. This is one of them. This is one specifically for hypothesis design and development. And so you can see what the expectations might be, again, adapt it to your own particular course objectives. But again, don't reinvent the wheel when certain things exist out there would be my best advice. There are a lot of tools that can help get you through that. I will briefly just say that I also do this in my lab, in my courses, my lecture courses. This is a hat tip to Hal White, who is Professor Emeritus at the University of Delaware. I won't go through all of this other than to say I also have a rubric that evaluates students on their ability to ask good questions. They're reading scientific papers and asking questions about those papers. And so that's where this exercise comes from. And if you want to know more about that and kind of some bigger ideas about fostering curiosity, I encourage you to read this essay that I wrote in ASBMB today. This was in 2021, where I try to make the case for why curiosity should be an integral part of a chemistry curriculum or biochemistry curriculum. One of my favorite quotes then is by Levi Strauss, who said, you know, a scientist is not a person who gives the right answers, they're the one who asks the right questions. And so with that, I'd like to thank you all for your time. And in the spirit of Claude Levi-Strauss, I'd be glad to answer questions that you all have.
Thanks, Dan. That was wonderful.
Thanks. I get it. It's the end of the day. I get it. Well, it's the end of my day on East Coast time, or it's lunchtime, right, for other folks. Or somewhere in the middle.
It is. It is. I love the curiosity and the generation of questions, and in terms of implementing that. And what context in your lecture classes do you put that? Is that directly related to papers you guys are reading, or how are you applying that in the lecture classes?
Yeah, thanks for that, Jess. So the way that I teach, our students solely read scientific papers, and they create biochemistry content from reading that paper. So for example, the one we're going to talk about next is How the Mongoose Can Fight the Cobra. It's a story about evolutionary pressures on changing the nicotinic acetylcholine receptor, and how that results in lower binding of the snake toxin to the receptor. And so that paper talks about central dogma, right? So you're looking at cDNA and how that gets changed, how that turns into changes in amino acids on the surface of that receptor. We talk about northern blots, western blots, and kind of basic binding sequence alignments. And so the students see all of this at once, which can be really overwhelming. So this is scaffolded. We do much simpler things in the beginning of the semester. But eventually, when they read this paper, they might not know about a bunch of those techniques, but they may say something like, figure 2 is a northern blot. What is a northern blot? How do you get RNA? If it talks about RNA being in there, how do you design a probe? What am I looking at? And by asking those questions, if they're well asked, right, which is the key part, that by answering those questions, they would teach themselves something about what northern blots are, and presumably about oligonucleotide design, and perhaps even radioactivity and other aspects. So, you know, one of my favorite things I share with my students is I have a 12-year-old son who will sometimes say, "Dad, did you see that?" And I'm like, "That is a poor question. I have no idea what you're talking about." So let's talk about context. Let's talk about giving me a clue, what you really want me to know. And so, yeah, so we do a lot of that kind of foundational work early in the semester, so we can get to the part that I just shared with you by the end of the semester.
So Dan, there was one comment in the Q&A,
yeah, wonderful,
a little bit back from Greg Caputo, who said, and I think this was in response to your prompt about problems with teaching STEM. He said, teaching STEM in ways that focus on a specific method to get the answer, rather than embracing many ways to get to the answer.
Yeah.
And I think that's a really good comment.
Yes. No, absolutely right. And I've been wrestling with this just recently. So, and I think this speaks sort of to appreciating that folks think in different ways, right? So for example, we just talked about a paper on acetylcholinesterase, and in that paper, they talk about histidine being shifted to a higher pKa. And so students ask, well, how can that possibly happen? And so we talk about it from Le Chatelier's principle. We talk about it using Henderson-Hasselbalch. If you want to go from a quantitative perspective, we can just talk about the straight up kind of understanding those as an equilibrium and doing an oral way of talking through that. But it's a really good point that Greg makes, that we, you know, the more we talk sometimes we give this false sense that there's only one way of knowing and one way of doing things, when in fact there are multiple ways at getting some sort of content, right, or some sort of conceptual understanding.
Right, and that prompt tickled my memory banks, and I remember a slide that I show at the start of my cures. I think the quote is from a faculty member at Harvard, but the quote is, "The best learning occurs at the edge of chaos."
Yes.
And I use it to explain that, you know, I have no clue at the moment where this class is going to go, because we're going to come up with ideas and test them and think about them and try and learn things. And then that feeds into the fact that often in a cure, we're really talking about, once you've got the question and you know what it is, you've thought about what it is you're trying to measure, it's sort of a just-in-time learning type process where you then have to go out and find whatever approach is going to give you the information to answer the question. You know, it's more than this sort of rote, well, we're going to do spectroscopy today, we're going to do chromatography tomorrow and whatever. It's not just to gallop through a bunch of techniques. It's thinking about how do I get the information that I need. So I'd appreciate everybody's comments, especially Dan's on.
Yeah, that's a great point. I'll throw out one quick one, and then I'd love for other folks, because I think we are in a time and place where we can kind of broaden discussion. One of the experiments that we do is a competitive ELISA. And so students will come up to me with a standard curve with a negative slope and insist that they did something wrong. So they're really quick to feel that they don't know what they're doing, as opposed to being curious, like, why would this be a negative slope? To me, that would be the natural question. Why is this upside down? And instead of saying, why is it upside down? It is, oops, it is upside down. It's not supposed to be, therefore I'm wrong. And so that leads to really interesting conversations about, well, let's talk about how that ELISA works. And once they start drawing it out, then it's like a light bulb goes off and like, oh, so I am competent. I just didn't think about what my experimental protocol was and what I was looking at, right? So, yeah.
Yeah. So there are two more questions that have just cropped up in the Q&A that I want to bring up and get people to respond to. So Joseph Chen is asking how experimental results obtained by students from these cure type labs can be compiled for publication as components of research articles, either as pedagogical research or biochemistry research, and what sort of challenges are involved in moving from results obtained in a lab to getting a publication out of it. I know a bunch of you have thought about that. So anybody want to take that one on?
With the silence, I'll jump in quickly. Hopefully that'll start some others. I assume this means scientific publications on the basic science, not necessarily pedagogical.
Yes, let's address it from that perspective.
Yeah, so I will say that, so what Basil has been talking about is, I don't know if you're familiar with this micro publication, and the idea is it's a one-figure publication. And so we've been talking about that might be something that's achievable in one semester. And really, if it's a 15-week lab or a 10-week lab, if you're quarterly, you could think about just doing one experiment with one figure and structuring the writing of a manuscript around that also, right? So it's skill development on top of that. The nice thing about micropublications is that they also freely admit that you can use those data for a bigger publication at some other point. So you can either reference or use that data again, but that's a possible solution. I know other colleagues of mine, I'm envious of my microbial genomicist colleague below me, who can turn out data like crazy, right? And that's, the time scale of cures are very different depending on the data scale that you need, right, are very different depending on the cure.
Right. Any other thoughts, or we'll go on to another question? So the next question that cropped up in the Q&A, how do you get students interested in the lab work, especially ones who are planning to go to medical school and don't see the importance of research? And I think that's where, and I'll start by making some comments, that's where the topic of the research project really comes into play. I teach a course that's an introductory chemistry course, but it's about drug design for anti-malarial drugs, much like Regina teaches a course that's involved in things like this. And the minute you put those sorts of things in the title, and you get students to think about the relevance of that topic, I think they buy into it much more. And in fact, at the end of my course, I have a hard time turning down people that want to come work in the research lab. And it's a great way to get students into your research lab, is to teach a course that's got that sort of. So Regina, I suspect you've probably had the same.
Yes, and for sure, the work that's done with the students in the sophomore level organic chemistry class. So this is Dwight Williams's class. That really gets a lot of students interested, and regardless of where they're headed beyond Kalamazoo College. So definitely that's the case. And for example, my senior level MedChem course, which is all computer-aided drug design, we spend the first part of our 10 weeks learning how to use computational tools. And they are literally there this week. They have to come up with what problem do they want to work on? Is there a drug? And once you do that, you know, a lot of them think about drugs that they're either personally taking or their grandparents take, and they begin their project there. Once you make it personal and medically related, they do engage. And so I find that what the topics are of what you want to add makes a difference, which also brings me back to getting them engaged younger rather than waiting to say the senior level really gets them engaged early enough in thinking about doing research. So.
Yeah, absolutely.
Yeah, if I can just kind of add to that, maybe. I think the flip side is also true. Sometimes I worry about students who do research, medical students who do research for the sake just of doing research and putting it on their CV, and the folks that the spots that the opportunities that then takes away from folks. So I think it's worth asking, right? Why do students not want to do research as well? And why do they want to do it in the first place beyond just you know, I need to do this because it's expected of me in order to get into medical school or whatever, right? Graduate school or whatever. And a lot of this comes back to that intrinsic motivation. You know, the first couple of research experiences I had were not because I was necessarily interested in it, but somebody said, you know, you have value and you should be in my lab. And then only after that did I then find my path to what kind of was my passion area of biochemistry, molecular biology. So, you know, I haven't found a really good way of phrasing it, but of course, from this curiosity framework, I would think, well, I would want my medical doctor to be curious and have a mind of, well, what is going on here and what approach might I take to curing your issue, right? There are certainly things that are straightforward, others that just appear to be straightforward. And so, you know, sometimes I've had that conversation with my students too.
Can I add, Dan, part of what I'm discovering? So the CUREs sort of takes away the everyone has to do research. So that really helps students understand before they even come and ask, what is it really going to be like when I work in the lab? But what I've discovered is that in my current biochemistry majors class, because I have biochemistry majors, but they're heading to medical school, I try to also explain to them that the tools we're working on and learning in the wet lab setting will help them think about solving problems in a clinical setting, right? So they don't, the patient doesn't come in and say, I know I have strep throat. Can you please tell me that I have strep throat? Right? The patient comes in and says, I have this problem, and you have to learn how to ask those questions, as you pointed out, Dan, and troubleshoot and connect some dots. And for me, when I teach the majors biochemistry class right now, they begin with a plant source and an E. coli source. So we begin there, and then they move from there, understanding that you have to sort of ask those really good questions, and it's not simply that you're going to go do research. So yeah, it comes back to what questions you are asking and helping them think about, right? Back to sort of
right. We've got another good question just popped up in the Q&A from Kristen Ramsey. Do you envisage CUREs as a substitute for more traditional biochemistry courses or as a supplement to them? And I certainly view them as an almost essential supplement to them. I would also argue that actually, and some universities, Columbia, I think, is now doing this, where every student, irrespective of their major, has to take a CURE in their first year. They have to learn about how to do research, how to do whatever. So any other?
So can I just quickly say, for me, it's on top of, right? So there's the course, and then all of the stuff we do for cures, we do in the lab. So it's a supplement to learning biochemistry.
I mean, I would say, and this is kind of the approach that I take with my biochemistry class, because there's a lot of content that we don't cover. And my approach for that class is similar to the approach that I take in the lab, because in the lab, of course, with a lot of the iteration, we cut out a lot of weeks where we could be covering other things. And I would argue that it's more of about an approach. I mean, how many of us have taught ourselves the things we need to do in lab or in our class because we needed it at the moment, right? Might not have been perfect, but if you're empowered with a process, then you can get pretty far or find the resources you need to get far. So, so yeah, to some extent, I would say, I'm not saying that that's the only way to do it, is to do cures or authentic inquiry labs, but I think there's a great place for it in terms of building self-confidence and resiliency and you know, giving them the feelings that they can in fact find the information that they need to attack a problem that they may not yet have found, come up against.
Right. Well, we're coming to the end of our time, so I need to share my screen and make a few closing remarks.
Hey, Ellis, there's one last question from Jala Asibo.
Oh, okay.
You want me to ask it really quickly?
Yes, please go ahead.
How are students who generate the data recognized in publications? Should they be considered as co-authors?
My answer would be yes. And we're actually in the process of writing a paper that's got contributions from 3 different cure classes, and about 60 students are going to be co-authors on this paper. And we've seen that happen in other cure consortia as well. So I don't know whether anybody's got any other answers to that, but it's a good question. Okay, so we've come to the end of our allotted time, and I wanted to thank all the participants that have been on this, because you've been asking some great questions and prompting some good discussion. But I want to especially, can everybody see my screen okay? Yep, good. I want to thank the Protein Society and their staff for letting us do this. If you've sat through the whole of this, you've probably worked out that we all enjoy working together and talking with one another. And that's one of the great things about the cure communities that have grown up. They're communities, and we all have common interests and we work together. And I particularly want to thank my co-presenters. I won't go through all their names again because you've met them all, but you know, without you guys, this would not have been anywhere near the webinar that it's been. And I think it's been a lot of fun with some great discussions and points. So the last thing I want to say is that, you know, one of the things that usually happens after a session like this is people want to know how to get involved. And so there's a couple of answers here to that. One is to join one of the consortium groups we've talked about. There, you rarely find they say, no, we don't want any new members. You know, we all like the community. We're all interested in expanding. The other is start a cure based upon your own research. You don't have to join a community. You can start a cure based upon your own research. And our cures community, which is optimizing undergraduate research opportunities via cures, is there to really try and promote people developing cures, not just joining cures, but it's also there to try and coordinate pedagogical research. And, you know, please get in touch with that group if you're interested. And I'm going to speak for all of the presenters and say, we all love talking to people and interacting with people that want to help students. So please feel free to get in touch with us. So with that, thank you everybody. And that brings us to the end of this webinar. So thanks again to Raluca and the Protein Society staff, especially for helping to make this happen. It's been a lot of fun and we hope it's been useful to people. So thank you all. And with that, you can have your lives back, guys. You're a great group.